The concept of molar mass is an essential concept for general chemistry and for many other upper-level chemistry courses. We cannot count atoms. They're very small, they're too tiny to count, but we need to know how many there are. And the way you count atoms is by weighing them out, determining their mass. And this molar mass is that concept that gets us between the mass of that thing and how many you have. Now you watch a little video about how to order salami, and you don't order salami by how many pieces you want. You say, give me a pound of salami, and you get so many pieces with that. Give me a pound of, and pick up something, and you know how much you have by weight. For atoms, we do the same thing. We don't count them out, but we need to know how many we have, and we use weighing them out to determine that. Okay, so what is a mole? A mole is, and here is its definition, it's kind of a strange definition, it is the number of atoms in exactly 12 grams of the isotope carbon-12. That was arbitrarily established. They decided they would determine how many were in 12 grams of carbon-12, and they counted that out. No, they didn't. They experimentally determined that out, and they came up with the concept of the mole. Now, a mole is nothing more than a number, a word that means a number, and it's that number. Now, grasping that concept, for some students it takes a little time for it to sink in, but it is nothing more than a number, okay? It is a number like the word dozen is a number. That is not a hard concept for anybody to grasp. If I said, give me a dozen eggs, you don't sit there and go, dozen? What's a dozen? I don't know what that is. A dozen, instantly you think 12, okay? The word gross is a number. It's a dozen or 144. It is a word that means a number, okay? And a mole is a word that means a number. Now its definition is kind of crazy, okay? But there is a number of atoms in that 12 grams, and it is a number. Okay, so they went and experimentally determined what this value was, and that's the value, 6.022 times 10 to the 23rd. A huge number. That number is kind of a pain to say, 6.022 times 10 to the 23rd. That is how many atoms are in 12 grams of carbon-12, okay? And they said, okay, we're going to take that value and we're going to assign it the word mole. This is a mole. Just like we said, 12 is a dozen, 6.022 times 10 to the 23rd is a mole. That is called Avogadro's number because of the scientist who determined it or came up with the concept of measuring how many you have by weighing them. And so we call that Avogadro's number. Avogadro's number is a lot easier to say than 6.022 times 10 to the 23rd. So Avogadro's number, the mole, and 6.022 times 10 to the 23rd all represent the same quantity of something. Okay? It doesn't have to always be in carbon. It can be other things, but that's what a mole is. Oh, there's going to be something important here in a minute. Let's see what that is. All right, so there is this thing that we call a molar mass. We don't want to deal with carbon-12 anymore, but we could do with any substance, okay? A molar mass is the mass of 1 mole of that substance. Now, it can be a mole of atoms. It could be a mole of molecules. For this lesson, we're going to focus on elements and atoms and not on compounds and molecules. We'll focus on those later. Okay? So, the molar mass of carbon-12. It says here that the molar mass is the mass in grams of 1 mole. Well, look back at the definition of a mole. A mole, by definition, is how many atoms are in 12 grams of carbon-12. So that's its molar mass. Okay? We wrap right back around, okay? You might want to stop and ponder what I just said. Listen to it again. Molar mass, because of its definition, and because of what we've defined a mole as, we know the molar mass of carbon-12 is 12.000, forever O's, grams. All right? Now, if you just want plain old carbon, what you do is you go to the periodic table. And that periodic table is a weighted average of all the isotopes, not just carbon-12. It has carbon-12, carbon-13, carbon-14, and it's its weighted average. And when you look at that value on the periodic table, you see 12.011 grams. okay? Now, prior to our discussion of molar mass, when we saw that 12.011, we said that's the average mass in AMUs of an atom. But we're up in the scale, and we don't want to deal with individual atoms anymore. And we don't want to deal with that tiny, tiny unit of an AMU. We want to get into a world that we can actually feel and measure. And that's why they came up with this concept. They wanted to get out of that individual atom world. They wanted to get out of the mass of AMUs, which is so tiny, and get into a world that we can actually feel and measure and see. And that gives us our molar mass, okay? So this is the important thing. The molar mass in grams of any element is numerically the same thing as the atomic mass in AMU units. So you go to the periodic table and you look at an element. Let's look at the element helium, okay? If you look at the element helium and you look at the value given there for it, and we've thought about that in atomic mass units, one atom is this many AMUs. But if you up the scale to a whole mole of them, then we'd have 4.003 grams in a mole. So we have this many AMUs in an atom, and we have this many grams in a mole. Now we can weigh that out, we can measure that out, and then know how many we have. If we measured out 4.03 grams of helium, we would know we would have 1 mole, or 6.022 times 10 to the 23 atoms of it. So we can now look at that periodic table and quit thinking of them as masses in AMU units and start thinking of masses in gram units, and know that it brings along with it a whole bunch of those atoms. Okay, so here are some relationships that we have learned. A mole of atoms is 6.022 times 10 to the 23rd atoms. A lot of atoms. A gram equals this many AMUs for this exact same reason. If the relationship from atoms to moles is 6.022 times 10 to the minus, or to the 10 to the 23rd, then the relationship between AMUs and grams is that same relationship. One atom, so in the world of atoms, one atom of carbon-12 weighs 12 AMUs, and if we up the scale, 1 mole of carbon-12 is 12 grams. So it's kind of a summary of those concepts that we've talked through so far. So now we're going to apply this information to doing dimensional analysis problems, okay? Unit conversion. Whenever we have a fraction, like we have here, for a unit, we can use this guy to convert between those things, okay? So we're going to do some dimensional analysis here, all right? So these are glorified ones. What do we mean by that? When we see this number, 4.003 grams, and 1 mole. That is what this means. The same quantity is in the numerator as in the denominator if we're talking about helium. This many grams of helium and 1 mole of helium would be the same quantity in the numerator, the same quantity in the denominator. So this is a glorified 1. It can be used as a conversion factor. So its job is to convert us between grams and moles. Whenever we have a molar mass, we can go between grams of that thing and moles of that thing. Now you can't go from grams of helium to moles of water. That doesn't make sense. You can't go from grams of lead to moles of gold. That doesn't make sense. But as long as you're dealing with the same substance here, you can use the molar mass to convert between grams and moles of that thing. And there is, like I've done here, the relationship between the one that we used as a definition, carbon-12, and 12 grams of carbon-12 is 1 mole of carbon-12. But notice it's the same substance in the numerator and the denominator. This is our glorified 1 that we can use as a conversion factor. Okay? So when we go to a periodic table, we don't usually write the molar mass as 4.0 and cover that up. I can't cover it up from this side, but 4.003 grams and only write that. We write it as grams per mole because that's the relationship that that molar mass will give me. So it's not the only unit factor that we've learned about in this little bitty lesson here, okay? What else have we seen already in this chapter? We now have a relationship between the moles and the number of atoms, okay? So in this example, I'm using carbon-12. You can go between moles of carbon-12 and atoms of carbon-12. That relationship would happen for any substance. I could do the same thing for helium. 1 mole of helium is 6.022 times 10 to the 23rd, and since this is an element, we're talking about atoms of helium. If this were a compound, we wouldn't be talking about atoms, we'd talk about molecules, which we'll do later. But for now, we'll always go to the atoms because we're dealing with elements. Okay? So you can replace that. As we see here, we had the moles of carbon-12, and I've replaced it with helium. You can replace that with anything. You could replace it with plain old carbon, okay? It wouldn't change the numbers. You could change it to helium. It wouldn't change the numbers. You could change it to oxygen. It wouldn't change the numbers because there's this many atoms in a mole of them regardless. You could use water molecules, okay? This 1 mole of water is this many molecules of water. Since water is a compound, we wouldn't talk about atoms. You could deal with elephants, okay? 1 mole of elephants is 6.022 elephants. It doesn't matter. You could do donuts. Okay? You could do basketballs. Doesn't matter. That's what 6.022 times 10 to the minus 23rd to the 23rd. I'm sorry I keep saying minus. 6.022 times 10 to the 23rd. There's a bunch of them for every 1 mole. All right, so we have both of these unit factors. We've got going between grams and moles. We have going between moles and the actual number. In this case, it's atoms. And we can, with those two things, always convert between these in either direction, okay? Whoops, don't want to back up. You could do back arrows, and let me do back arrows over here on the screen real quick. I could go this way as well, okay? So if it could be laid down in any one of these places, either here or here or here, I can find out the other two by using those relationships. And we're going to practice doing that. I'm going to go ahead and write that relationship that we see at the bottom of the screen up here on my board so that we can point at it and refer to it. We can go between grams of an element, okay? We can go from there to moles of the element, okay? So we're going from grams, moles, and then we can go to, from there to the number of atoms. We can go through and do those 3 conversions. There's 2 conversions to go between 3 items. Okay, so let's practice doing this. First one I will do in its entirety for you. The others you'll try, and then I will see how you did and show you the work if you didn't quite get the right answer. So how many atoms are in 10 grams of oxygen? So we're going to start with 10 grams of oxygen. Now later we'll learn that oxygen is a diatomic molecule and we'll write it as O2, but I'm just talking about I've got 10 grams of oxygen and I'm just using the elemental symbol oxygen. Now we're going to go from grams of oxygen. Where can I go? The only place I know I can go is to moles. So I'm going to go to moles of oxygen. Now where do I go to get that information? Anytime I'm trying to determine the relationship between grams and moles, I write them down first as units, and then I go to the periodic table and I find the value for the atomic mass or the molar mass of oxygen, and I see that it's 16. Now by definition, that's how many grams are in 1 mole. So I will always put that number with the G, and I'll put the 1 with the mole. And then I will go from moles of oxygen, so I was sitting right here, I'm ready to go to atoms because that's what it's asking for, is how many atoms do I have? Well, I'm going to write the units down first. I have moles of oxygen, I'm going to give myself plenty of room here. Atoms of oxygen, gave myself plenty of room because by definition a mole is a bunch, 6.022 times 10 to the 23rd. Okay, so now we're ready to multiply that out. Now many students, not many, I don't know how many, but there are students that don't use their calculator correctly. I'm going to post a little video on how to use a simple TI-30 calculator to make sure that you are using your exponent key correctly here. But when you multiply this out, the value that you will get will be, and let's see if I can find it, 3.76 times 10 to the 23rd. So you ask yourself, is that reasonable? Should there be a whole lot of atoms in 10 grams? Well, if you understand what a mole is, then yes, you would understand that it's a whole bunch of atoms. Okay, so the next one is, what is the mass of 1 mole of aluminum? Okay, stop and put in an answer. Okay, so you know whether or not you got it right, but I want to ask you, how did you think about that? Some people might have done some actual work, but let me ask you this. If you go to the periodic table and you look at the value for aluminum on the periodic table, you will see that it's 26.98. All right, 26.98 is the molar mass. That's grams per mole. Okay, so what's the definition of a mole? Molar mass, the mass of 1 mole. So if I had 1 mole, I really don't have to do any work if I understand what molar mass means. It is the mass in 1 mole. But let's say that you didn't quite figure that out. You could start with 1 mole and say, okay, I've got a mole. I'm sitting right here. I'm trying to go to grams. So what do? I cancel the moles. Okay, I go to grams. I look at the periodic table and I see that there's a 26.98 value given, and I always put that with the G and the 1 with the mole, and lo and behold, yes. Okay, I end up with 1 times this divided by 1. But I want you to just pause for a moment and think, what does molar mass mean? It is the mass of a mole. So if you want to know what the mass of a mole of anything is, just go to the periodic table, look at that number, and you know the mass of that mole. Okay, you try this one. Okay, so you either got it right or wrong, but let's go through and work through it. A million. What is a million? A million is 1 times 10 to the 6th. Okay? And you're not just writing the number down, you're writing a unit. And you're not just writing the unit. I recommend you get in the habit of writing a unit and the substance it is, because eventually we'll start switching substances. Here we're staying in iron the whole way. But if you get yourself in the habit of atoms of what and writing it down, it'll be a good thing to do. So we're starting here at atoms, and we're trying to get to the mass. Now it doesn't say what units mass. I'm going to get you to grams, okay? We could go to pounds if that were asked, but since it didn't ask, any old mass unit will do, and we can go to grams. So we're going to go from atoms of iron, oops, Fe. All right, so where can I go? I can go to moles. So I go to moles of Fe. Okay, now I'll get my units down. Now I'm ready to put my numbers in there. A mole, by definition, is, 6.02 times 10 to the 23rd atoms. Okay, now I'm at the moles, and I'm ready to go that last step, and that would be to go to grams. So I don't want moles of iron. I want grams of iron. And I go to my periodic table. I look at the value for the molar mass of iron. It's 55.85. I have to make sure I put it in the right place. Molar mass is the grams in a mole. By definition, how many grams are in a mole? So now, make sure you stop and put this into your calculator and see if you get this answer. Because if you don't, very likely you're using your calculator wrong. You should be able to put this in without using parentheses. If you're having to use parentheses to get a right answer, you are giving yourself a lot of extra work. There's a way to use your calculator that you can plug these in right down the line, and you can get the value of, let's see, what is this one? 9 times 10 to the minus 17. It's a very tiny amount in grams of iron. Okay? You might think a billion is a lot. I'm sorry, it's not a billion, it's a million. You might think a million's a lot of atoms. It'd take you a long time to count that many out. But in the world of atoms, it's not very much at all. It would only have 9 times 10 to the minus 17 grams of iron. Too little to even feel, okay? Now, your last question is, how many moles are in 62.5 grams of helium? Okay, so here's me working through that problem. 62.5 grams of helium. I'm sitting at grams. It's just wanting me to go to moles. It's a one-step process. So I have grams of helium here. I have moles of helium here. I know that this is a relationship that's called molar mass. I go to the periodic table and I put it where the G is. There's this many grams in 1 mole. And that's how I obtain the answer of 15.6 moles of helium. Okay, quite a few moles of helium because it's a very, very lightweight element. All right, so we've worked through possibilities of going in any direction here. You've got to get this down in your mind. You will use this over and over again. Eventually we'll drop off the atoms and stay just here, but you always need to realize that when you're talking about moles, you're talking about how many, in the same way that when you're talking about having 3 dozen donuts, you're talking about how many donuts you have. If you're talking about 3 moles, you're talking about how many atoms you have or how many molecules you have. So we have to realize that conversions that we can do are like we have tools. I don't want you to memorize, what do I not want you to do? You know, have this down and say, okay, I can only do these things. Every one of these things are tools that you have in your tool belt that you can pull out and use whenever you need to use them. And we're kind of growing our list of things that we can do. We learned today how to go between grams and moles using molar mass, how to go between moles and the actual number using Avogadro's number. Earlier, in Chapter 1, we learned how to go between grams and milliliters using density. And we learned as an example using our prefixes that we can go from the base unit to any prefixed unit using the definition of our prefixes. So these are things that we are going to keep in mind that we always can do. That when we need to go between grams and moles, we'll go to the periodic table and get molar mass. If we need to go between moles and atoms, we use Avogadro's number to do that. We have to get familiar. There is some memorization at the beginning as you're getting used to what tools do I have and how do I use them. But then we should be able to let you put them together in whatever fashion is needed to solve a problem. Now you're going to try this one here. And I would like for you to think about their molar masses and come up with the answer not by doing a bunch of calculations. You can if you have to, but see if you can come up with an answer by thinking about the mass of each of these things and not by thinking about the calculations or doing the calculations, because the same calculations in all. So I want to write on the screen the molar masses of each of these. Gold. Gold is a big fat beast, okay? It has a molar mass of 196.97, that's its grams per mole, okay? Aluminum is a little bit lighter, okay? 26.98 grams per mole. And neon is lighter than that, okay, by a little bit, 20.18 grams per mole. Okay? Stop and think about that and choose an answer. Okay, so which one's going to have more atoms? Well, they all have the same mass, but they don't weigh the same. And so they're going to have a different number for each one. The one that has the most is answer C. So I'll circle C here. That is going to have the most atoms in it, even though they all weigh the same. Now, let's think about this in terms of this image, this next image here. Number versus mass. I've got marbles and I have peas, and I have the same number on the left side and I have the same number of peas as I have marbles. There's a dozen. But we know that marbles per pea weigh a lot more. So this is kind of the opposite of the previous problem. If you have the same number of each one, the one that weighs more per item is going to weigh more. Okay? So a mole of light atoms would have less mass than a mole of heavy atoms. And that's kind of the opposite concept of what was done in this problem. Here we have the same mass on both pans. Okay, so let's draw out the scale. Okay, and let's just choose two of them to compare. Let's choose these two. So I've got 14 grams balanced out with 14 grams. They weigh the same. They're balanced out. But these guys here, the gold, are much heavier. It takes fewer to reach 14 grams. As this guy that's lighter, it's going to take more of them counted out. Now, if you have a hard time seeing it with that, let's think about fruit, okay? And let us measure out 2 pounds of fruit. And we want to make 2 pounds on both sides, so we're going to make sure that they balance out. On the left side, I'm going to put apples. And on the right side, I'm going to put grapes. Both of them are going to be 2 pounds. Now, which one's going to have more pieces of fruit? Here, we've got maybe, to get 2 pounds, I don't know, maybe we have to have 5 pieces of fruit to get up to 2 pounds. But over here on the grapes, these grapes are small, and it's going to take a whole lot of these grapes, a whole lot of them, before I ever get up to 2 pounds. So the lightweight, guys, it takes a lot more. Lightweight, okay, whoops, lightweight fruit, heavier fruit. It's going to take a lot more pieces of fruit to weigh the same. In the same way, it's going to take a lot more of the lighter guy to weigh the same, to have the same mass as the heavy guy. So we can relate our substances by way of their mass. How many do I have by mass? If we go back to the beginning of this lesson, we'll see that they entitled it Counting Atoms by Weighing Them. And that is what we're doing. And you've got to keep that always in mind when you're using molar mass, is you're trying to get a relationship between how many you have and how much it weighs.